I just need to, it's going live now. Texas Server, yeah, and then I just need to pause the other one because we have a few seconds delay on the other side. One second, there you go. Mute it, and then the same thing. Thanks. Let me share here very quickly. All right. So let me begin while people start trickling in California time, Berkeley time. You can see that welcome once again, everybody, from the break of Finland to the online SPIN+X seminars. As you know, this is a webinar type of seminar. Please write your questions down during the talk, and I will give you the word afterwards, so you can ask the questions yourself to the speaker. We have all the things scheduled up to the end of June, and we're going to continue schedule with July. If you have any suggestions of the speakers that you think would be appropriate for this audience, let us know, please. And let's briefly introduce you the speaker today. James Analytis is a Charles Kittle Chair in Condensed Matter Physics at Berkeley. I would be very scared to fill as a chair, you know, given Kittell's reputation. But he is a very broad physicist. He actually is very well known for his work on topological insulators and also strongly correlated systems and conventional superconductor, critical phenomena. You name something interesting, he'll be involved in it. And recently, where he's done some very interesting work in looking at antiferromagnets on how to manipulate them or make them connect to some correlations. And this is a little bit of what he's going to tell us about. So I'll stop sharing. And I'll ask you to please go ahead, James, and start sharing your start whenever you like.
Great. Thank you, Jairo, for that introduction. Yes, so as Jairo pointed out, I'm currently a professor at University of California, Berkeley, and I'm a condensed matter experimentalist. I'm delighted to be giving a talk at SPICE. I've been following the seminars during the pandemic, and I have to say it's been a refreshing and constant staple of that's keeping at least some of the scientific creativity of my group alive, because it's been critical to have that connection to our community. So thanks again for inviting me. I'm going to tell you about an interesting problem that we started a little bit over about 2 years ago on a particular class of systems, but I'll start the actual problem that I'll describe from a 60,000 foot point of view. What I'll tell you about is the collective dynamics of coexisting spin textures and how they connect to antiferromagnetic switching, the particular kind of material, the ion intercalated TMDs. So for those of you who know me, the kinds of things that I'm actually typically involved with in my research is looking at strongly correlated systems. And in there, it's really the study of different kinds of interactions between electrons, whether that's exchange interaction or Kondo interaction, Coulomb, spin orbit, all those kinds of things, and how they play into understanding the overall properties of a material. The emergent phenomena that comes from exotic systems. What we end up studying is, of course, the ground states, the equilibrium states that emerge from those kinds of interactions, whether that's a charge-ordered system, an antiferromagnet, or something more exotic, like a spin liquid, or sometimes a superconductor, or a pneumatic system, or something like that. And we usually study the response functions to see whether there's something interesting and unique there, and what that can tell us about the underlying Hamiltonian. That's generally the way my group works. So in order to expand on that, how we got into this particular problem, let me start with what we're really trying to understand in reaching these kinds of ground states through these number of these types of interactions is really the physics of phase transitions. And just to, and particularly phase transitions associated with spin. So I have here what you would expect from an ordinary magnetic system at very high temperatures. All the spins will be paramagnetic and pointing in any direction. And then as a function of lowering the temperature, those interactions start to become noticeable, and those spins will order in some interesting way. And this is very analogous to what you see, for example, in a liquid to crystal transition in liquid water. We have a phase transition at some critical temperature as those water molecules start to interact. In the case of a magnet, you will often end up with either a ferromagnet or an antiferromagnet or something even more exotic. But the point is that the state, once you get to that low temperature state, is characterized by some kind of equilibrium state, a little bit like one of those ground states that I described earlier. And so at T greater than the critical temperature, all of the spins are disordered. And then at some low temperature, they find this equilibrium state. And in general, because there's more than one possible configuration, you end up having domains. So in a ferromagnet, that'd be spin up and spin down. In an antiferromagnet, that'd be nail vector oriented one direction or nail vector oriented in the other direction. And that equilibrium state, from a local perspective, is actually completely independent of the history of the system. The number of domains might depend, but in general, the whole point of an equilibrium system is that it doesn't know anything about how it got there. So that's kind of one signature of the kind of ordered state that we might study here. The other signature is, of course, that there are collective modes in a ferromagnet. They're known as magnons, where the stiffness of the spins themselves start to create these low energy modes that can transport things like spin, for example. Okay. Now let me contrast that with a different problem, one that isn't described as an equilibrium state, at least in the classical sense, in the typical sense, I should say. And that is when and that is the problem of quenched disorder. This is the kind of thing that comes up, for example, in the liquid to crystalline transition when you supercool water or some other liquid, and you're basically cooling it faster than the time scale for the system to equilibrate. And if you do that, then you end up having some static configuration at low temperature of the water molecules, or whatever the molecules might be, the liquid molecules might be. And you've quenched, in effect, the disorder, some kind of disorder in the system. Now, in a magnetic system, there is an analog of this kind of supercooling, which we call, which isn't completely identical, but it's similar. And that's what we call a spin glass. Now, in the case of a spin glass, it's not necessarily that you have to supercool a system. It's just that there's no actual time scale slow enough for the system to actually equilibrate, because there are so many long time scales in the system. And what you end up there is that you very much get an equilibrium state, or a low temperature static state that is dependent on the history of the system, and you actually get a distribution of possible configurations of equilibrium states. You can think of them that way. Rather than having a single kind of equilibrium state, like we did in an antiferromagnet or ferromagnet, you actually have a distribution of them. And in that case, there's really no concept of a domain structure or anything like that. So that's all very interesting, and you might be wondering why I'm telling you about that. And that's because it'll tie in very closely to the kinds of physics that I want to tell you about for the intercalated TMDs. But one part that's really interesting about spin glasses and quenched disorder system is actually what happens to the collective modes. We saw in ferromagnets those collective modes are magnons, but there is actually an analog in these of collective modes in a spin glass, and that's when and you can imagine that even though the system is not magnetically ordered, it's still stiff in the sense that the spins talk to each other. So when you rotate one, it'll have an immediate effect on rotating its neighbors, and then going forward from there. And this was described by in a paper by Bert Halpern and David Saslow, where they studied the free energy associated with this kind of collective motion. And they divided the free energy into two main components, one of them to do with the local magnetization density around a certain region. That's what basically alpha corresponds to. And obviously dependent on the magnetic susceptibility of the system. And then the other energetic term is, of course, the stiffness of these spins and how and what their local rotation angle actually is. And so by solving the free energy, they discovered there are these hydrodynamic modes, which are effectively the equivalent of the magnon in the superconductor, in the ferromagnet. The result is that these kinds of collective modes can actually transport angular momentum. They can actually transport spin, even though the system is not in a kind of equilibrium state that we understand very well, like a ferromagnet or an antiferromagnet. As far as I know, though, no one's seen like really clear evidence of the existence of these modes, although there have been some certain indications that they might be there. So the kinds of materials that I want to tell you about today have both antiferromagnetic order, but they also have some coexisting spin glassy behavior, or at least things that seem to be consistent with a spin glass. And that's what makes the kinds of systems, the antiferromagnetic switching that I'm going to tell you about today, a little bit different from the classical examples. Okay, so in order to just to introduce the materials, let me tell you what they are. They are a very large class of magnetic systems. They are the intercalated TMDs, and you can intercalate them with a large range of different kinds of materials. You can choose all of these magnetic elements here in the center of the periodic table. You can change what the transition metal in the chalcogenide is. You can also change the chalcogenide itself from sulfur and selenium. So there's like a really large variety of possible systems. They form a triangular lattice, which means that frustration is often a problem, but I would actually see it rather than frustration as an opportunity. And in fact, I'll come back to that towards the end of the talk. Okay, now, before I got into this class of materials, although obviously a lot of people are still studying transition metal dichalcogenides in the Van der Waals context, but actually, a lot of measurements have been done on these materials by none other than Stuart Parkin and Richard Friend back in the late 70s and early 80s and others. And a lot of work had been done both in the magnetic properties, but also in their magnetically ordered, understanding their magnetic order. So on the left, I've shown the magnetic susceptibility of these systems. So you can see that they're magnetically ordered around 40 or so Kelvin. What the susceptibility, the two curves shows the interplane and out of plane. And what this basically shows is that because the susceptibility is so much larger out of the plane, which they've labeled as H parallel here, it suggests that the spins are actually mostly oriented out of the plane. Now, in terms of the magnetic structure, there was also determination around the same time of what the magnetic structure would look like, and that you can imagine the spins are actually pointing north and south on this diagram. But actually, it turns out that this magnetic structure is a bit controversial. So a couple of decades later, there was another magnetic structure determined that saw, instead of this word-side or zigzag type structure, actually saw a stripe type structure. You don't have to remember that until the very end, but it's important to know that the magnetic structure was actually wasn't very well understood. I think until myself and our collaborators actually explored the system in detail. Okay, so what is an antiferromagnetic switch? I'm sure for this particular community, I don't have to introduce this in great detail. See, there's a question in the question and answer.
Don't worry, we will do that afterwards.
Oh, okay, we'll come back to it. Okay, great. All right. So for those of you who are familiar with this kind of work, you'll know that the basic idea is that is essentially inherited from the way we understand spintronics in the ferromagnetic context. But in this case, you have an antiferromagnet where the spins are staggered, let's say in the square lattice. And from this, you can actually define, from the difference of the sublattice magnetization, you can define what's known as the nail vector, which points in one direction. And the whole idea is that, let's say your system breaks inversion symmetry. So it either happens at an interface or the system breaks inversion symmetry in the bulk. Then when you apply a current, an electrical current, you end up getting due to the spin orbit coupling, and perhaps there's a strong rash bar term in the system, the broken inversion symmetry in the system, so given by this polar vector Z, allows you to have a electrical current that's very slightly spin polarized. And because it's slightly spin polarized, you can actually impart an angular momentum onto the antiferromagnet itself. And the result of which is that you can actually rotate the nail vector from one direction to the other. And that's what we mean by the switch. It's not that you're turning this antiferromagnetic order on and off, you're rotating the antiferromagnetic order from being oriented in one direction to being oriented in a perpendicular direction. Okay, so again, I won't dwell on this too much because I'm sure there's actually quite a bit to get through, and and I'm sure a lot of this is familiar to many of you. But the way this is understood, or the dynamics of it, is what's known as the Landau-Lifshitz-Gilbert equation, where you have two components with which we understand the rotation of the spins of the antiferromagnet, and that's what's known as a field-like term and an anti-damping term. Here you've got the magnetization, which is the local magnetization of the spin in the system. H effective is the effective field in some sense applied by the spin polarized current. And the basic idea is that this effective field term is helping you rotate your spin in two ways. One, by a typical M cross H term, which is the way we think of a real external magnetic field affecting our spins. And then a second term, which actually creates precessions of the spins around an axis. And actually that anti-damping term can also rotate your nail vector, sometimes even in the same direction as this field-like term. Okay, but it's in general a relatively complicated process, but I think mostly it's understood, certainly in the case of ferromagnets. But we inherited this language from the ferromagnetic spin torque systems and applied it to antiferromagnets, and now this M, instead of applying to the magnetization of the system, now applies to, let's say, the sublattice magnetization of the antiferromagnetic system. Okay, so in a seminal paper in 2016, Wadley, Jungwirth, and others created these kinds of devices where you could actually apparently observe the rotation of the nail vector using this kinds of system, with theory by Zhelezny and Hyro himself, which motivated a lot of these experiments. But in this particular experiment, what you're looking at here is that you can apply current in two orthogonal directions, the black direction and the red direction. And what's happening is that the nail vector is in principle being rotated in the central region between one orientation and the other orientation. And you can detect this using a read current in the 45 degrees, where you can essentially measure the resistance changes in the central region. And whether it goes to a high resistance state or a low resistance state tells you whether you've rotated the nail vector one direction or another. Okay, hopefully I didn't get too much of that incorrect. So this is what a typical signal looks like. You will pulse current in the red direction, so that's the north-south direction, and you'll see resistance changes getting more and more closer to a lower and lower resistance state. Then you apply in the black direction, and you'll apply multiple pulses in that direction, and it'll go to a higher and higher resistance state, and so on. And applying a higher current again, you can kind of get to what looks like a saturated value after many pulses. But this kind of sawtooth-like structure is quite typical of these kinds of systems. The same was seen in the manganese 2 gold, which was actually one of the original proposed materials by the theory, where they see a similar kind of structure, except now it's hundreds or more pulses, and you just keep going into the higher and higher resistance state or lower and lower resistance state. So there's a lot of work, and I would say pretty clearly demonstrated that something interesting like this is happening. Now, why do you get the sawtooth-like structure? Again, there's probably people here that can explain this better, but my understanding is that we basically think that most of the effects happened at the domain boundaries. And so by applying multiple pulses, you can shift that domain boundary further and further along. And so you can change the resistance state from the nail vector in one direction to the nail vector in the other direction. So that's the basic understanding. Now, there was a bit of a different take on not these particular systems, but interfacial systems, where people suggested that there might be heating, that there was could be also a source of this kind of switching. So there was a paper by Chang and others that appeared at the end of 2019, where they did a similar experiment, but actually on a dummy substrate. And what they showed was that just through the heating caused by the electrical pulses, you can actually get a very similar kind of sawtooth type structure. So the point of that paper really was that there needed to be some that multiple effects might be happening when you're doing these kinds of experiments. Okay. So let me just take you to one of the main punchlines of my talk. Here's a similar cross-shaped material device made of iron intercalated niobium sulfide, shown on the left here in false color. We made this not by thin film or lithographic techniques, but actually using focused ion beam. So we took a single crystal, made a lamella, and machined out these little arrows, and then basically copied the same configuration that Wadley and others used in their 2016 paper, but now did it on a single crystal, because we didn't have thin films of this material. So now we have the blue pulses in the east-west and the red pulses in the north-south, and you get the same kind of switching from up and down, just like you would expect: high resistance, low resistance. In other words, it seemed to work in this material as well. The material breaks inversion symmetry, it has antiferromagnetic order, and it seems to go from this high resistance to low resistance state when you apply these current pulses. What was kind of interesting, that is somewhat of a difference with these other systems, is that it didn't matter how low or high current we applied in these pulses. We always seemed to get a saturated resistance. In other words, we never saw the sawtooth-like structure. It was more like a telegraphing type structure that we saw, where you just basically, after multiple blue pulses, you just get one resistance, multiple red pulses, you just get one resistance, and so on. So this was a little bit different from the other systems in that sense. Which I point out here. The other difference is that the currents that we had to use were actually very, very small in comparison. So mostly the currents seen in these, that you had to use in these pulses to rotate the copper manganese arsenide, for example, are around 2 orders of magnitude larger current density than what we had to use for our systems. So that was a bit of a surprise as well. The second part is that there's also a really non-monotonic current dependence. So here's the resistance change that you see. So this is one of the pulse trains. So what you're seeing here is just one of these pulse trains squished in for different current densities, and I have different current densities applied for each one of these pulse trains. And what you see is that the switching turns on, then somehow turns off again, and then turns back on again. And you can apply the same trick with, instead of using current density, you can actually keep the current density fixed, but change the pulse duration. So how long you apply one of those current pulses with, and you get a very similar kind of effect. It turns on, then turns off, then turns on again. So this was also, we didn't understand this, we just published it, but there was certainly something very unusual going on. But I'll come back to that because I think we have an answer now. And before I go on, let me just say there's one other way to understand what's going on and connect it with the antiferromagnetism. And that is to look at the effect of an applied magnetic field. How am I doing for time, actually? Let me just check.
Yeah, pretty well. Another 20 minutes.
Okay, good. Excellent. So Yeah, I think at this stage, it's probably good to just introduce one other parameter, which is how the system responds to an applied magnetic field. So remember, I showed you when we were looking at the Landau-Lifshitz-Gilbert terms, one of the terms was like a field-like term. So you actually do expect that maybe by the application of a magnetic field, you can also orient the nail vector in the same way, just by coupling to the anisotropic susceptibility of the antiferromagnetic system. And so by applying a magnetic field, you can actually also shift those domain boundaries in an antiferromagnet. And then you can also change the angle of the magnetic field in the system, and then see how that compares with your angle, with your switching of your electric field. So here's the angle dependence of rotating that magnetic field in the plane of the sample, and here's the resistance that you get if the blue resistance is the longitudinal changes the longitudinal resistivity. The red resistance is the changes to the perpendicular resistivity. And you can see that you get this very nice sinusoidal like behavior, which is basically telling you that you're able to orient those, change those domain boundaries so you can see the changes in the anisotropy of the conductivity tensor. And you can plot this in a polar plot, to show this angle dependence directly. And what we found is that, well, I'll skip this part. What we found is that the angle dependence of what's called the anisotropic magnetoresistance matched perfectly with the angle dependence that we see in our applied electric field. So whether you apply in the where you pulse in the north-south or east-west direction and then rotate that around the sample, you get the same kind of angular dependence as you would if you applied a magnetic field and rotated that around the sample. In other words, the electric field and the magnetic field must be having the same kind of effect on rotating the average nail vector by shifting those domain boundaries. So the reason why I bring this up is because the anisotropic magnetoresistance will become, in some sense, an independent measure of what we're doing to the nail order that I'll come back to in a second. Okay, so that's one of the punchlines. We have this nice intercalated TMD. You can switch it like an antiferromagnetic switch by applying these relatively low current density pulses, and it seems that you're doing what the theory tells you should be doing, which is rotating the average nail vector. But there's a few things that we don't understand. We don't understand this anomalous current dependence. We don't understand why how the magnetic order connects to the rotation of the nail vector. Particularly, you might remember, I purposely mentioned that the nail order, the spin polarization, was actually mostly out of the plane, but the magnetic field and the current that we're applying is actually all in plane. So this wasn't completely obvious, and it still isn't completely obvious to us as to why it works, whereas all of the other antiferromagnets that we could switch all had in-plane magnetic order. Okay, so there's lots of things that we don't understand. So now let's go a little bit of a deeper dive. So or does it correspond to the magnetic order? So the deeper dive takes us to, as I mentioned there, intercalated TMDs. And instead of just looking at one stoichiometry, which is thought to have one magnetic order, let's do the full gamut and go from under-intercalated to over-intercalated. So what we're playing with there, is, let me just go back to the slide here. What we're playing with here is how many iron atoms are in between the layers. And at 1/3, that's where you have the stoichiometric structure. That's where you have the perfect triangular lattice of the magnetic ion, the iron atoms, and everything else just has defects. You go under, you have more vacancies. You go over 1/3, you have more interstitials, presumably. So we thought what we would see is just more disorder in the systems by just changing this intercalation. But you actually see something a lot more interesting. But before I get to the more interesting stuff, let me just show you the basic measurements. So here's a system going from under 1/3 to around 1/3 to over 1/3. So going from the stoichiometric structure to and disordering it in either direction. And I've shown you here in the top row heat capacity measurements across the magnetic transition, and in the bottom row magnetization. And you see exactly what you'd expect for the effective disorder on a magnetic system. When you add disorder, you strongly suppress the heat capacity anomaly. So near 1/3, it's a very, very sharp heat capacity anomaly and broadened either side. Similar effects in the magnetization. You see a very, very sharp transition near stoichiometry, but it broadens when you take away some of the iron and create vacancies, or when you add iron and create more interstitials. So disorder is bad for the antiferromagnetism, it seems. Okay. But with that, let me take you to something that's a bit more interesting as to how this connects to the switching itself. The sample that we used in our first paper was actually not perfectly stoichiometric. And this is more of an accident. We thought it was 1/3. We measured it to be 0.31, but we thought, okay, well, we still see this, the switching. Probably we can make the systems more perfect by going to 1/3. But we didn't think that the disorder actually had anything to do with it. So this was the data that basically I just showed you. And what you're seeing here is the temperature dependence of one of those pulse trains. So at the nail transition, those pulse trains start, and you start to see the switching between up and down. Again, it really shows you that it's connected to the antiferromagnetic order, the switching that we see. So because the signal grows like an order parameter and it saturates at lowest temperatures. So that was fine. Now look at the over-intercalated samples. Sure, the pulse trains turn on at around the nail transition, just as you expect, but then it kind of levels off, and then at some intermediate temperature that I've called TF here, it starts to turn on again. Now I want to emphasize, there's no phase transition that we know of at TF. There's no other kind of magnetic order that turns on there. And then we tried the sample with the sharpest heat capacity anomaly, with the sharpest magnetization transition, and looked at its antiferromagnetic switching. And what you see is basically a null signal. In other words, even though the sample is more perfect, to use an American expression, the system doesn't seem to switch really at all. Let's go back to the magnetization and try and figure out what's going on, particularly with the sample here. What was that intermediate temperature, TF? So if you look closely at the magnetization, you actually see the zero field cooled magnetization and the field cooled magnetization split here. The reason why that's important to tell you is because the difference between zero field cooled and field cooled is that there's a different history, right? If you cool the system in a field, it has a different history than if you cool it in a zero field. For an equilibrium state, where you have just a pure antiferromagnet, it shouldn't care whether you field cooled it or zero field cooled it. It's in its equilibrium antiferromagnetic state or it's not, and it doesn't know what its history was. But a spin glass does know what conditions it was cooled in. And that's what we think is happening at this intermediate temperature. That's where the spin glass is somehow freezing. And if we can look at dynamics, so the other signature of spin glasses that you expect, some long time scale relaxation. And so, and that's what I've shown on the inset here, that around this temperature is where this long time scale relaxation seems to onset. And that's where the switching somehow blows up. That's where you start to see this growth over here. But how does this relate to the other samples? Oh, I don't have that. Yeah. So how does this relate to the other samples? Well, let me just go back a slide here. For the under-intercalated one, the splitting happens at much higher temperatures. So in other words, it becomes glassy very close to the nail transition. So we probably wouldn't have noticed that difference. And for the perfect sample, the one right near stoichiometry, there's never any signature of any kind of spin glassy behavior. And there, we don't see any signature of any switching either. So I think disorder is involved. And I think that's very interesting. But it's not the only thing, as we recently discovered. But let me just summarize that part with this slide. Now, on the top row here, I have the anisotropic magnetoresistance. What I showed you before is a signature of the presence of the role of the magnetic order. And what you see in the anisotropic magnetoresistance is no signature of the spin glass whatsoever, and especially in this X equals in this over-intercalated sample. So the anisotropic magnetoresistance turns on at the nail temperature just as you would expect it to, and then just saturates. It doesn't care that there's a spin glass there turning on or around this freezing temperature here, but the switching somehow does. Okay, so why is that? Well, we think it connects to the first part of my discussion, which is the role of having a coexisting collective spin texture. What happens when you have an antiferromagnet that's stiff in itself and has its own well-defined equilibrium states, coexisting with a spin glass that doesn't have an equilibrium state in the same sense, but it does have collective behavior. And so the idea is that when we apply the spin polarized current, we're not just imparting angular momentum directly to the antiferromagnet, but we're actually imparting it to the spin glass as well. And because the spin glass texture is there, it's opening up another channel with which you can actually transport angular momentum, with which you can actually impart angular momentum onto the antiferromagnet. And that's perhaps why the efficacy of the spin transport grows as soon as the spin glass is frozen, as soon as stiffness for the spin glass sets in. And the theory for this is also not completely unprecedented. I've already told you that the collective modes are thought to exist from Halper and Saslow back in the 70s. But there was a nice work by Ochoa and Jaroslav Czekorniak, who in 2018 showed that these collective modes could indeed carry angular momentum. Okay. So let me now take you, so that was kind of a lot to digest probably all at once, but let me take you to a different part, which we recently discovered. So we did some work with Bob Bergeneau and his postdoc Shan Wu, looking at the neutron signatures of these materials as you change the intercalation. And I mentioned earlier that there was some controversy about what the antiferromagnetic order actually is in these materials. Before I tell you what their results are, let me tell you about one nuance which I found very surprising. For the underintercalated samples, the ones with the vacancies, you can have construct a device with this geometry where you go from a low resistance to high resistance, low resistance to high resistance, where the green and red are basically associated with whether you're pulsing east-west or whether you're pulsing north-south. If you go to the over-intercalated samples, so add some extra iron basically, and you have the same geometry, somehow the east-west pulses become high resistance and the north-south pulses become low resistance. In other words, exactly the opposite to what you see in the underintercalated. Let me emphasize how bizarre that is. There's already a lot of bizarre properties, but let me emphasize how important that is, because if the magnetic order is, the nail order is basically the same, and you wouldn't have expected it to be any different between one intercalation and the other, given it's really just disorder that is changing, at least in principle. You'd expect the same kind of spin polarized current to rotate the nail vector in exactly the same way. But what this would be saying is that for the same geometry, the only thing that's changed is the disorder. The nail vector is actually being rotated oppositely for the systems with different intercalations. And this is where the determination of the magnetic order became super important. First, let me demonstrate that this really is associated with the magnetic order. What I've shown you here is the current dependence of at different specific temperatures as you go across the nail transition. And so at the nail transition, you start to see the pulse train turn on. And what's interesting is that as you go to colder and colder temperatures, the current you need to apply to turn on the switching becomes higher and higher, which basically tells you that the current at which you see the switching is the minimum current, the threshold current, is a proxy for the order parameter. It measures the antiferromagnetic gap. All I need to do is rotate this, and you can see very clearly that it looks like an order parameter growing. So the switching threshold really turns on like an antiferromagnet. But why would you have opposite kinds of behavior between one intercalation and the other? Well, the controversy in the literature was between two different kinds of magnetic order, both anisotropic. One of them is stripe order, and the other one the zigzag order. The zigzag order was the one determined in the early 70s by Rietveld. The stripe order was a more recent determination by another group in the 90s. And we wanted to get to the bottom of which magnetic order was actually in the system. Well, you can guess that it's both. So in the underintercalated, it seems that that the magnetic order is dominated by the stripe-like order. In the overintercalated, it seems to be dominated by the zigzag-like order. And in the stoichiometric compounds, well, you turn out to have both order parameters involved. What you're looking at here, of course, is just the reciprocal space intensities of the neutron scattering ray vector, and as a function of temperature, then this is plotting that temperature dependence of that reciprocal space point. And so for the stoichiometric compounds, you seem to see both kinds of intercalation, both kinds of magnetic order. So it's very natural then, a very natural way to explain what we were seeing in the switching. We were seeing switching of one kind with one sign for the underintercalated. We were seeing switching in the opposite direction for the overintercalated. And for the stoichiometric compounds, it seems like these two things basically cancel. And they cancel because both kinds of magnetic order appear to be simultaneously present. And we've done some extensive DFT calculations with Jeff Neaton's group and Sophie Weber, where we showed that the stripe order and the zigzag order are actually very, very close in energy. And in fact, it's only a difference in the next nearest neighbor interaction that actually allows the system to switch from having stripe order as the preferred state to having zigzag order as the preferred state. So we think that's probably a natural explanation for why the switching turns off for the stoichiometric compound, and also why it has the opposite signs for the endpoints, for the underintercalated and the overintercalated. What's still remaining is the microscopics, of course, like how the spin polarized current couples to these magnetic orders, and again emphasizing the moment is actually interplane. So again, like how it couples to this Landau-Lifshitz-Gilbert equation is still perhaps not completely transparent. And so let me just end with one final thing, which is the anomalous current dependence. So what I've shown you here is fixed pulse width, and then this is the threshold current. And what we noticed that was very interesting is that at some threshold current, about 6 kiloamps per centimeter squared or so, you have this large increase in the switching, and then if you increase the current, then you have this somewhat of a decrease and then kind of a saturation. And you see the same kind of thing with the pulse width as well. So fixing the current density and changing the duration of the pulse, you see this large increase and then a sudden decrease and then kind of a saturation. This is not natural in the typical antiferromagnetic switching perspective. You have a threshold current, and then once you're over that threshold current, you can always rotate. Here, there's some preferred threshold current, and then every one after that is suppressed. And you can actually plot this in a color plot, in a contour plot, and you can see that this threshold current really kind of follows a semicircle. Why would this be? Well, we think maybe the results of Shan Wu and Bob Bergeneau might help explain this also. If we have two order parameters simultaneously present, one going in one direction and the other one switching in the other direction, then what you're seeing here is probably just the addition of the two. So a large increase when one turns on at the threshold current, and then suppressed by the coexisting other order parameter, which is going in the other direction. So this might be a natural way to explain this bizarre current dependence too. Okay, so that takes me to my summary. I do have some extra slides that I could show you, Jairo, but I'm not sure if you want to just go to the Q&A now. It's up to you. I think I finished a bit early, but I think most people will forgive me for that.
Yeah, I think up to you. There's many things we could start the questions. Then you can extend if the questions go in that direction. I have a feeling.
Did you want me to end? I've spoken 45 minutes.
If you have a few more, if you think it's going to be important for the story, do you have a few more minutes? Of course.
No, actually, I think this is probably a lot of information to download.
Yeah,
so
a lot of people will be asking questions.
Yeah.
Okay.
So just let me summarize. I had no clue that the system would be quite as rich as it was when it came to the antiferromagnetic switching. Certainly not. I didn't anticipate that such a small change in stoichiometry would actually change the nature of the antiferromagnetic order. And there's a lot of more interesting things to do that I can tell you about offline as well. But certainly disorders involved, and certainly the coexistence of different order parameters is involved as well. So after that, I'll be happy to take your questions, and thank you for your attention.
So thank you very much. That's very exciting new material and lots of things to understand. So let me start with James, actually. So James, go ahead and ask your question, please.
Hello, can you hear me?
Yeah, I can hear you.
Hi, that's very, very interesting. So one advantage that's typically claimed for antiferromagnets is their faster speed of dynamics and hence potentially faster switching speed in devices. And if I understand correctly, you suspect these hydrodynamic modes are assisting the switching in this particular material. So my question is, what are the timescales associated with these hydrodynamic modes? And how would you expect that to affect the speed of the switching possible in this particular antiferromagnet?
Yeah. So when people talk about the speed of the antiferromagnetic switches, usually what they're talking about is the precession dynamics of the spins in the antiferromagnet, which are determined by the exchange energy J. The way this changes in this case is that the dynamic still remains fast, even in the presence of the spin glass, except now you're looking at an average J. So you shouldn't be too deceived by or too perturbed by the very long timescale dynamics of the relaxation of the system that you see in a spin glass. That can take a very long time to equilibrate, simply because you have so many different you have so many different timescales in the interactions of the systems, but the average J can still remain high. So in the end, you can still have very fast dynamics, but it won't be as fast as a pure antiferromagnet. But the average J can still remain pretty high. But the thing that I would say in terms of the response time of these systems, so I mentioned to you earlier, like in terms of the switching, the DC switching that I've demonstrated here, although I'm not sure what exactly determines this timescale. So maybe Jairo can actually answer this question. But remember how I mentioned that you could, for these particular systems, they turn on at a much lower current density than typically seen in other systems. They also turn on at a generally lower pulse width as well. So we start to see some switching at around, a few microseconds, for example, of pulse duration. So I think that is more getting over a threshold of how much energy you're kind of dumping into the system than it is to do with the speed of the dynamics. So I hope I've answered your question.
Within your experiment, you cannot tell. So let's say Daniel, go ahead and ask your question, please.
Yeah. My question is mostly about the structure, how to visualize.
Hi, Daniel. How's it going?
Yeah, hey. That you argue that you have a kind of coexistence of antiferromagnetism and spin glass. How should I visualize it? First part of the question, how to visualize it? Is it really in the same part of space, or it's kind of in homogeneous state like phase separation? In some parts of the sample, you are mostly purely antiferro, and some other parts are more disordered and maybe responsible for spin glass behavior for all this relaxation and so on. And related question, actually, it looks like this pure stoichiometric material, which exactly 1/3, is actually the most disordered magnetically. That's actually what you have shown with one of the previous slides, when you have this complicated behavior on neutron scattering at exactly stoichiometric material. Wouldn't it mean that in fact what you call stoichiometric material is actually in homogeneous state in which part of the sample are slightly underdoped, other part of the sample are slightly overdoped? So on the average, you have looks like exactly 1/3, but especially in homogeneous, so parts of the samples are kind of striped, part of the samples are zigzag. In that sense, I would expect that just this, what we call stoichiometric material, would behave most unusual. But in your current measurement, if I remember correctly, we have this behavior which you attribute to spin glass only for overdoped material, not for stoichiometric. So in other words, the main question is actually how homogeneous are these materials in different concentration range? Is it really space separated states or what?
You're muted. James, you're muted.
Yeah. We've done some nuclear magnetic resonance experiments to try and see what the local environment of the spins actually was. And from all of these experiments, so you apply magnetic field, you look at the precision of the nuclear moment, and that can tell you what the local environment is on average. And excuse me. What we found, so here what the NMR signal looks like as a function of magnetic field. Oh, by the way, done in the high field lab in Tallahassee. What we found at high temperatures, these peaks that you see are actually connected with the nuclear moment of the niobium, so the niobium 9/2 moment. And in all intercalations, you get a very well-defined nuclear moment. In other words, it seems that the moment that we detect has a very similar environment in all of the intercalations. And otherwise, what you'd normally see if there's multiple environments is that you would see multiple splittings, is my understanding, from the same moment. Whereas we see this basically the same environment, no matter what the intercalation is. The second thing that we see is that as you decrease to lower temperature and you go to the antiferromagnetic state, we see two broad peaks associated with essentially the spin up and spin down configuration of the antiferromagnet. Now, this would probably be agnostic to whether it's stripe order or whether it's or whether it's zigzag order, assuming that the ordered moment remains the same and the exchange, the local exchange energy remains the same, I suppose. But again, we see this the same kind of splitting in each one of these intercalations. The only difference is, so the under-intercalated and the over-intercalated that you see here, so those are actually have been cooled in field. And there you see that there's a moment that one of the peaks, so that's corresponding to spin up, for example, is bigger than the other peak, which corresponds to the spin down. That's because the defects are aligning with one of those environments. That's the way we've understood it. So in other words, the defects are kind of seeing the local environment of the exchange energy, which is the same seeing the local environment of the antiferromagnet, and they see the same kind of environment as the antiferromagnetically ordered spins. So the defect spins see the same environment as the antiferromagnetically ordered spins. So from these kinds of local measurements, we don't seem to see multiple environments that the magnetic ions see. We just see, we just observe that every moment has the same kind of environment. So from these measurements, we don't have any evidence of macroscopic inhomogeneity. It seems that all the moments have the same environment, local environment. Now, but it doesn't quite answer your question to the stoichiometric compound. Yeah,
exactly this one.
Yeah. So here, you know, in the end, there has to be some kind of phase separation. But what's interesting is that we don't have any evidence of any kind of Glassy behavior for the stoichiometric compound. Even though you have multiple order parameters that coexist and presumably have their own domains, we don't have any like relaxation dynamics or any long time dynamics that we do see in the samples that have been deliberately disordered, which have, you know, just one order parameter. But we don't have any history dependence of the magnetization or anything like that. So as far as we can tell, there's no Glassy-like dynamics for this environment. We just have two coexisting order parameters, and everything else is very sharp. Remember, I also showed you the heat capacity, the magnetization. We have the sharpest, the most delta-like heat capacity anomaly, the sharpest magnetization drop. So to me, it doesn't seem like there's magnetic disorder in these systems. It just seems that there's two order parameters.
But these are crystal systems, right? These are crystals.
Single crystals. These are single crystals.
Have you done the neutron scattering on them, or did I miss something?
That's what you're looking at right here.
That's exactly what it is, right? So then,
yeah,
if it was separated, it would actually, you would see the two peaks, but I don't see the two peaks. It's just, yeah.
Maybe related, not related, but very short question as to the structure. Stoichiometric material is 1/3. They are chiral. So from plane to plane, this orientation of this triangular lattice of cobalt is kind of rotated by 120 degrees. Does it play any role in what you study? The chiral structure.
It's a really good question. So the initial motivation for looking at the structure was because of the broken inversion, but it was mainly to get the spin Hall effect, mainly to get the Edelstein effect to work. We wanted the current to be slightly spin polarized. So that's why we chose this structure. How it affects the magnetic structure, I mean, as I said, we've done some extensive DFT, and you really only get these two nearly degenerate ground states, the stripe and the zigzag. I thought, because my experience in other inversion breaking systems is that you always get some incommensurate structure on top for many inversion breaking systems, like the skyrmion type systems and things like that. So I was hoping that that's what would happen, but actually we don't have any evidence for it. The neutron scattering hasn't seen any incommensurate in plane structure.
Sorry, let's go to another person, and then we'll ask it back again, because I'm going to ask about XML deep afterwards. But Mohammed, maybe you could follow up with your question.
Yeah. Hello, can you hear me?
Yeah, we can hear you. Go ahead.
Let me thank you for the informative talk. My question is about the residual entropy for a spin glass system, especially at low temperature. Some spin glass system has fluctuations below the critical freezing temperature. What is your strategy to solve this problem?
That doesn't sound like a problem. It sounds like an opportunity. What do you mean?
Change the spin. I mean, if you look at the spin configuration for a spin glass system, if we have residual entropy, the spin-spin correlation may be different, and the spin correlation can, effect to history dependent of the magnetic structure, I would say. And it's very good, I know, but sometimes it behaves like a noise. You miss the previous state and you are facing with the new state. Is it possible for you to tell us what is your strategy to solve this problem?
Yeah, again, I don't really see, I'm not sure if I fully understand the question, but I think if I understand you correctly, the problem is like understanding what the final spin configuration kind of is, in the presence of a spin glass.
Exactly.
Yeah. Our strategy is basically the myriad measurements that we've done. So we've looked at the neutron scattering to understand the equilibrium state. We've looked at the NMR, the nuclear magnetic resonance, to understand what the local environment kind of looks like as a function of disorder. And so far, we don't see, and we've done like, I don't know if structural disorder is an interesting thing to know as well. But as far as we can tell, we've done a lot of TEM work as well. And even though sometimes there seems to be disorder in the stacking of the layers, the actual layers themselves seem to be very well crystallographically ordered. But anyway, your question's really about the magnetic structure. And our strategy is really just to try and get some microscopic measurements, and I feel like that's what we've done. And as one of the take-home points that I wanted to make from the talk was that the spin glass, although it's problematic in the sense of complicating how we understand what's going on at low temperature, it nevertheless has some collective dynamics of its own. That's what's exciting about it. It has these Halper and Saslow modes that, might never have been detected anywhere else, but presumably there's some collective behavior when a spin glass goes stiff. What that seems to have done is open up another channel of spin transport. And as far as we know, that's the only way we can understand this very unusual temperature dependence of this over-intercalated sample, where you start to see the sharp growth of the efficacy of the switching without there being another magnetic transition of any sort. The only thing that's happening at this lower temperature here, where you start to see a growth in the switching, is that the spin glass freezes. The collective dynamics of the spin glass turns on. So even though we don't understand it, it seems to do something cool.
Okay.
Thank you very much.
Let's have Igor. Go ahead and ask your question, please.
Okay. First, I wanted to ask about thermodynamical part, how magnetic order is changing with concentration, but it looks like you have answers in NMR and neutron scattering, but not completely. The problem is that maybe you have formation of some clusters between iron ions with changing of conditions, and their lifetime is different. That's what you see. What do you think about this?
So again, okay, so none of the TEM data, the transmission electron microscope data that we did, the microscopy that we did showed any clustering of iron.
Macroscopy, well, but it's a different scale, I think. If
you
have
see atomic resolution.
Okay.
You can see where the iron actually is.
Okay, and what is effective interaction between ions?
Well, that's where the NMR, the nuclear magnetic resonance, came by, and that's where we saw the same environment, even for the over-intercalated ones. It seemed that they had the same resonances as the antiferromagnetic spins. So it seemed like the intercalated ions saw the same environment as the antiferromagnetically ordered ions.
Okay, thank you. Puzzle is remain.
The puzzle remains, yeah. And I think that the biggest puzzle for me, it's really a question for the theorists on the call, is it completely obvious how a moment that is out of the plane can couple to the spin polarized current, which is presumably polarized in the plane? I think that's the part that I'm confused about, is how does the switching happen in that configuration? And also the single pulse saturation, I find that really surprising.
I mean, in an antiferromagnet, an effective field will make you rotate. This is the thing. I think you're mixing the energy intuition equations with the ones of the antiferromagnet. You know, a spin torque, spin injection into an antiferromagnet will actually make you spin around it, depending on the modes that you have. Actually, unfortunately, Helen Ramona is not here today, but she will watch it carefully and get back to you later. Oh, hang on, let's say
the anisotropy energy is huge. Like the anisotropy energy is like a millivolt. Like it seems. Yeah,
so this is a thing that we're puzzling actually. Did you do XMLD at the same time of these experiments as well, to look at the domain wall structures? Like, I mean, one of the things that they did in the experiments of the low currents on the manganese to gold and particularly the copper manganese arsenide is to look XMLD to see that the switching of the domains were at the low temperature, seeing clearly that you go from 90 degrees switching. Once you go to the higher temperatures, then of course the switching is just not related to this Néel spin-over torque. And in here, it's not so clear that in your case it would be related to the Néel spin-over torque. But now you've clearly shown now that it's connected to the magnetic structure, having those two types, which was the new result that I didn't know. It just sounds very interesting.
Yeah, that was the result that we got in the last 2 weeks. So
yeah, it's great. It's finally, because before, you know, it was difficult to say, okay, is it connected to that, or there is switching, of course, but essentially, what is the connection to the order parameter, to the magnetic order parameter? In this case, that clearly shows that connection. But I would have seen, given those ideas of having this mixed phase, XMLD would show you this real space delivery connected to Daniel's the question, to see where the domains would be, if it's homogeneous or not. Because sometimes the structure itself, the structural one of just where the atoms are located, is not going to tell you, but the XMLD may. Is that something that you guys can do, XMLD, in this experiment? I mean, of course, you have to.
It is something that we can do, because I've got the advanced light source just up the road.
Yeah, that's what I'm saying.
So it's not for lack of trying.
Well,
it didn't work, and we're still working on it a little bit. Part of the reasons why it didn't work is because the way we're fabricating these samples, we use the focused ion beam, which disorders that top layer, because you implant ions basically in machining the sample. So when we first tried it, we basically saw nothing.
Right.
The second thing, so now we've started to work on samples with our photo emission collaborators, for our photo emission collaborators, and also our STM collaborators, that you can cleave after the device is fabricated, so revealing a clean surface. And we haven't measured those, but you can imagine it's a bit of a tour de force, because, well, tour de force is maybe a bit extreme, but anyway, you have this device that looks like this, and this is 50 by 50 microns or so, and you want to cleave this little area that's 10 by 10 microns, so they have to come in with a stick and just pinch off that bit. So we had to machine it in a funny way, and those experiments are ongoing. Yeah.
Okay, that would be interesting. Let me know if you have any results later on that. Let's see. I think Yuri wanted to ask Pashkevich a question. Go ahead and ask a quick question. I will make that the last question, since for poor James, it's very early in the morning already, has been suffering, needs some more extra.
It's later in the morning now.
It's later now, yeah. Yuri, would you like to ask a question?
Okay, some question. I am trying to understand the coexistence of these two order parameters. Is it possible that you have some main component in the same ion, which is fixed like by a strong antiferromagnetic interaction, but another one which is fixed by some kind of anisotropy, can be accidentally directed in different, maybe perpendicular to the main component, and then you will have something like coexistence of two order parameters on the same ion, like spin glass for some small component and antiferromagnetic order on another one. It is possible if you have very special anisotropy, if you have a few minima of anisotropy along one direction, then you will have such kind of behavior.
That's a very interesting point. I imagine there's probably going to be a symmetry analysis that would rule that out or not, right? So I'd have to work out, like, we'd have to work out for these particular order parameters that we have, whether they, belong to the same irreducible representation or not, and whether they can coexist in the same place or they have to be separate. I guess that would help. But I don't think any of our measurements can rule that out right now. It's a good idea, Yuri. It's a good idea.
Great. I think with that, I'm going to stop live streaming there.